And I'll turn it over to him for talking about quantitative probabilistic relational Hoare logic.
Thank you for the introduction. This is a joint work with Martin Avanzini, Gilles Barthe, and Benjamin Gregoire. The main contribution of this work is a logic for reasoning about pairs of probabilistic programs in a quantitative way, which means that we are interested in finding upper bounds to mean values, probability values, and similarity metrics of pairs of programs that are written in imperative language with recursion and sampling instructions. While designing this logic, we had two goals. The first one was to be relatively complete for some classes of properties, and the other goal was to have a logic which is easy to use, so the user could compose proofs nicely, and we wanted the user to reason about probabilities only when it was strictly necessary. The applications of these logics are to cryptography, differential privacy, and machine learning, but I won't be able to cover any of these applications. You can find details in the paper. Before going to the main focus, I'd like to briefly introduce what you need to know about probabilistic programs for understanding this talk. So in this talk, we can take as probabilistic programs that are written in an ordinary imperative language, but that feature this instruction that sets the value of x to one of those between the braces with uniform probability. So for instance, if we have this program C that executes the command setting x to the uniform probability between 0 and 1, and we execute it on an initial state, we will have two transitions, one to a state where x is set to 1, one to a state where x is set to 0, with the same probability. If we add another sampling, the probability of the next sampling are independent of the probability of the first one, so we reach a total of 4 possible final states, each one with an associated probability of 1/4. So the output of the computation of a probabilistic program in this setting is a set of possible final states associated to a probability. On these distributions of final states, we are maybe interested in computing the expected value of some real valued function. So in this case, we may be interested in studying what is the expectation after the execution of the function x plus y. This value is given by the sum for all the possible 4 states of these terms, where the blue part is evaluation of the function on the term, and the green part is the probability of reaching that state, which in turn is the product of the probability of each transition. Expectations for us are important because our logic is meant to find upper bound to expected values. The reason why we decided to define this logic is to improve the expressiveness of another logic, which is pRHL, the probabilistic relational Hoare logics. In this logic, in pRHL, we have judgments that are relational because they talk about 2 programs at a time, and that are qualitative because the pre and the post conditions are 2 relations that can either be satisfied by a pair of states or not. The interpretation of this judgment is basically saying that if the initial states are related by R, there is a way to relate with S the final distributions. And the way we establish this is by requiring a coupling between the output of the program C and between the output distribution of the program D, whose support is included in S. So this means that if we sample from the coupling, we always obtain pairs that are in relation with S. But besides the definition of the interpretation of this logic, what is important to understand at this point of the presentation is that pRHL has been mechanized and has been widely used for proving correctness and security of many cryptographic applications. So you find those applications corresponding to the pink dots in the plot. But pRHL has 2 limitations. The first one is that the kind of judgments it has are not really suitable for reasoning about quantities. So for instance, if we want to reason about differential privacy, in pRHL we cannot do it nicely because we have pre and post conditions that are relations. To overcome these limitations, some logics have then been introduced in order to allow this kind of more quantitative reasoning. And another limitation of pRHL is that there are some judgments in pRHL that are valid but cannot be proven. Therefore, pRHL is incomplete. If we want to see an example of such a judgment, we can think of program equivalence. So in pRHL, we can express nicely program equivalence. For instance, the judgment that you see on top left of the screen says that the 2 programs evaluate on states that are related by R produces 2 equal final distributions, and this is our characterizations. However, in some cases,
using the pRHL proof system, this is something that we cannot show nicely. So for instance, if we take these two programs, we can observe that these two programs are computing the same distribution, which is the uniform distribution between 0, 1, and 2. The program on the left performs rejection sampling because it enters the loop, and then it exits the loop only when x is either 0, 1, or 2, while the program on the right samples from this distribution just by definition of the semantics of the sampling instruction. So for these two programs, we have this judgment, which says that on any initial input, the two programs compute the same output distribution. However, this is a judgment that we cannot show in pRHL. Therefore, we introduced our logic in order to achieve some form of completeness, in order to extend the expressibility of pRHL. We did it by changing the type of pre- and post-conditions that we are using in our judgments. So instead of having two relations, as for pRHL, now we are using two functions that are mapping a pair of states to a positive real. With this choice, we can now talk about quantitative properties. We also talk about expectation, because our semantics is basically expressing the fact that the value of the precondition evaluated on the two initial states is an upper bound to the expectation of the postcondition evaluated on some coupling mu of the two final distributions. And with this kind of judgment, we can already express some interesting quantitative property, such as, I went to the end, sorry. Such as, for instance, we can talk about expected values. This judgment is basically saying that when we execute x, which is sampling between the uniform distribution of 0 and 1, and when we execute that program that is setting y equal to 1, the expected value of x plus y will be upper bounded by 3/2. And this corresponds basically to the interpretation of the validity of this judgment. Another thing that we can do is reasoning about probabilities, because we can encode probabilistic events by means of this encoding to 0, 1 valued functions that are 1 only if the event holds and that are 0 otherwise. Then it turns out that the expected value of such an encoding is equal to the probability of the event that we are encoding. Therefore, the judgment that you see is basically saying that 1/2 is an upper bound that when we execute these two programs, the sum of x and y will be equal to 2. And another thing that we can do with our judgments is to put in the pre and in the post condition some logical variables that are variables that do not belong to the program variables of the two programs and that are universally quantified. This turns our judgments into schemas because they will be valid for every choice of f in this case. And for instance, the judgment that you see is telling us that the term on the left is an upper bound to the expectation of f of x plus y when we execute these two programs. And the nice thing about having logical variables is that the judgment is then valid for every choice that we do for the logical variables. And this extends the expressivity. Then we have a proof system for deriving our judgment. It is a Hoare-style proof system. I won't bother you with all the rules, just some key properties. The first one is compositionality. So we have this sequencing rule that it is composing these two proofs about two programs into a proof of the composition. And what I'd like you to observe is that if you're familiar with standard Hoare logic, you will notice that the pattern of the pre and the post condition is the same as in standard Hoare logic, which means that we can compose our judgments that are non-standard with some ease. And another thing that I'd like you to observe is that the sequencing rule, for instance, is not reasoning about probabilities. Indeed, the only rule that reasons about probabilities in our calculus is that for sampling. And what it does is also not so involved, because the goal of the rule is that of finding an upper bound to the expectation of phi. So the rule basically computes these expectations of phi for a given coupling of the two distributions and puts this value of the expectation in the precondition. Another property of this sampling rule is that it's comparing two structurally identical programs. So on one side we have a sampling, and on the other side we have another sampling. And if we only had these kind of rules, we could compare just programs that are structurally identical, and this would limit a bit the expressiveness of our calculus. So to overcome this limitation, we added also some rules that are one-sided, because they can be used to reason about
one program by leaving the other unchanged. So in particular, we can use these rules on top of a sequencing rule, where on one side we add a skip, because as I wrote in the bottom of the slide, we're always allowed to add a skip before or after a program in our calculus. And then by applying one of these rules, we reason about one program, leaving the other unchanged. And this allows us to reason about two programs that are not structurally identical. Just before I go ahead, by looking to these rules, you will see, if you're familiar with standard Hoare logic, that they are quite similar to the corresponding rule in standard Hoare logic. Then our proof system has two key properties. The first one is soundness, which means that every judgment that we can prove is actually valid. And for the opposite direction, we have some form of relative completeness. Indeed, we were able to show that if C and D terminate with probability 1, every judgment that has this precise shape that you see, if it is valid, it is also provable. But what are we asking by asking that the judgment has precisely this shape? Well, we are asking that the postcondition is given as the sum of two functions, a function phi and a function psi, whose value depends only on the output of C and on the output of D, respectively. And this is the only condition that we need on the kind of judgment for provability. However, this theorem, stated like this, doesn't tell us much about what we can do with our logic. And you may wonder what we can actually do with this logic. So I have some corollaries I can discuss with you. The first one, which is, in my opinion, one of the most interesting, is that our logic is complete, it's relatively complete, for showing pRHL validity. Indeed, the judgment in pRHL that you see in the bottom of the slide is equivalent to the judgment of eRHL, our logic, that you see in the table. Therefore, the validity of one of those judgments corresponds to the validity of the other. And in addition, I'd like you to observe that the judgment that I put in the picture falls in the set of judgments that our logic is complete for. Therefore, let me rephrase this reasoning. If there is some property that is hold and that can be expressed by means of a pRHL judgment, well, our logic is complete for proving that property. As a corollary, we have completeness for program equivalence, because as we saw before, program equivalence can be expressed as a judgment in pRHL. And then we have also some other results that are more towards the quantitative side. So for instance, we have completeness for total variation. Total variation is a quantitative metric that expresses how much two distributions are different. And if some delta is an upper bound to the total variation of the outputs of the two programs, the judgment that you see in the table is valid, and vice versa. And you see that the encoding is, again, one of those encoding that our logic is complete for, which means that we can always find also the precise value of the total variation with our logics. And another thing that we can do is measuring the epsilon delta coefficient of epsilon delta differential privacy, because what you see in the bottom of the slide is a definition of epsilon delta differential privacy. A program is epsilon delta differential privacy when epsilon and delta somehow bound the amount of information that the program reveals on its input. And the statement that you see in the slide, that is precisely the definition of epsilon delta differential privacy, is equivalent to the one that you see in the table. Therefore, we have this one-to-one equivalence. And again, the encoding is some encoding that we are complete for. And finally, we're able to find a characterization also of Kantorovich distances. So Kantorovich distances are a generalization of distances between pairs of states to distances between distributions of states, defined as you see below. And when the big delta is the distance between the two states is bounded by h, the statement that you see below corresponds to the validity of the judgment in the picture, where f is a logical variable, so where f is universally quantified. And again, that judgment is one of those judgments that our logic is complete for. So in conclusion, I was a bit early. I hope I convinced you that our logic is a quantitative relational problem logic that is expressive and composes nicely. And we saw that it is sound and complete for some interesting properties, like the validity of pRHL judgments and measuring the epsilon delta differential privacy coefficients. And in the paper, you will find other contributions, like rules for reasoning about recursion, loops, and adversary that are a feature of pRHL that I didn't discuss, as well as some case studies. So thank you for your attention. I'm happy to take questions.
Hi, thanks for the talk. I have two quick questions. First, could you go back to the previous slide?
Yes?
So in the encoding of pRHL validity, where does S come from?
I didn't say it. S is a logical variable, so S is quantified universally. So we must be able to prove this for every possible choice of S, and the type of S is a set of states. Okay. This encoding, if I can comment a bit of it, comes out from the quantitative extension of the Strassens theorem, and therefore, from that, we get the validity of the corresponding judgment.
Okay, great, thanks. The second is, so I know from like weakest pre-expectation calculus that the upper lower bounds often come from the treatment of non-determinism. So if there's a non-determinism in the program, they either take infimum or supremum to correspond to demonic or angelic choice, and so that's why they often bound. In your case, well, is there a non-determinism, and if not, where does the imprecision come from?
We don't have non-determinism. And the imprecision, I think it comes from the presence of the while. When you reason about a while, you need to find an upper bound to an invariant which is an upper bound. And there comes the imprecision. Otherwise, our rules are almost only doing weakest reasoning, so they are precisely
okay, great.
What
Thank
you
you.
expect. Thank you.
Great, we have time for a handful of other questions back there.
For pRHL validity, a more intuitive encoding to me was to have, in the post condition, have the intersection of the two sets you have, two events you have. Is this intuition correct?
Can you repeat?
Also, here in the post expectation, you have tau1 in S and tau plus tau2 not in TS.
Yes.
Is there also an intuitive encoding where you have tau1 in S and intersect with tau2 in TS?
I think there are multiple encoding of pRHL. Maybe the most intuitive one is the one where in the pre and in the post, you take the complement of the relations.
Okay. I guess my question is that are you encoding this way because for this to be complete, you need to sum up two things, each only using one of the program, and the other encoding not be complete?
Yes, that's the point. With this encoding, we can get easily completeness. Otherwise, we would need a rule that we have to switch from one encoding to the others.
Okay, thanks.
Thank you for the question.
Okay, we probably have time for one more quick question. Right here.
Right there, I think.
Great.
Yeah, so I was wondering if you've thought about applications to quantum programs, right? Because this does seem like it's the kind of thing that would lead exactly into looking at kind of expectation values of observables, and I know that's
I'm not working on it personally, but I know for sure that Gilles Barthe is working on it. So
I figured that's why I was asking.
So you can ask him this question. Okay.
Thanks.
Thank you.
Okay, great. Well, let's thank our speaker. And